Welcome to the sixth video of the Fortitudo.tech Python package walkthrough. In this video we'll be going through an example that uses the derivatives portfolio management framework. I'm really excited to go through this example with you because it really shows many of the nice features of our framework. So basically we have a comparison between variance and SIVA optimization using the derivatives framework and entropy pooling stress testing. So here you really see some of the many different features that are quite hard to do with other packages. So as always, we start at the front page of the repository and navigate to examples. And here you can see that example 5, this is the derivatives framework. So this example is the accompanied code for an article called Portfolio Management Framework for Derivatives. And basically the idea for writing this article came from working with buy-side people. So here I noticed that in asset management people tend to treat derivatives as if they are some alien instruments. So I've seen many unnecessary complicated way of working with them. On the sell side, people are of course very familiar with derivatives, but they are not so familiar with portfolio management, so they usually always report them in euros or dollars or something like that. So this article really brings together the different perspectives into one unified framework. So let's open it in our browser and then just go through some of the sections. So first of all, there's just an introduction, and then we have the presentation of the actual framework. So this framework is super simple and I also had some people tell me, oh, they did this 20 years ago or something like that, and I'm sure that someone has done something like this before, but the point is that when I try to explain it just verbally to people, then they will still confused, whether it was on the buy side or on the sell side. So I decided to document it in this article and then introduce some interesting analysis with entropy pooling stress testing. So here you can see that usually when you see something with portfolio management or portfolio optimization, then the self-financing constraint is expressed as something that portfolio weights needs to sum to 1. But in this article we argue that instead of focusing so much on portfolio weights, we should use something that we call relative market values and then exposures relative to portfolio value, and that this should be the self-financing constraint. The important point here is that this one, the usual constraint, is just a simple subset of this new constraint that we introduced, which is more general. So here there is some explanation of what these relative market values are and what these exposures relative to portfolio value is. So here you can really see it mathematically, so I'll let you read through it. In general, when we say exposure, we define it as the notional, and this is because it's quite easy to calculate the notional. Usually it's given in the derivatives contract, so you don't have to do any complicated computation to figure out what the exposure is. So here we just show some of the properties of the portfolio return, and actually the ideas for building a framework like this one were introduced in an article in 2010. The point is that in that article the framework is presented in quite general way with no real suggestions for how to unify everything. So this is what we improve on in this article by having a clear separation between portfolio weights and portfolio exposures, and have a practical recommendation for what you can use on multi-asset as exposures. So but these formulas with portfolio return are quite simple, and then there's a talk about how to introduce transaction cost and some perspectives on long-short portfolies that I will allow you to read for yourself. And then we come to this case study. So this is the one where we'll be going through the code and then see if we can get the same results and some additional nuances. So let's go back to the code and look at it here. So again, we just import the packages that we need, and we start by loading this log normal P&L that we have been working with before. So you can imagine that this is something that is like equivalent to a Black-Scholes model, because it also assumes that the P&L is log normal with this geometric Brownian motion. But in this P&L simulation, we do not have any options P&L. So the first thing we do is to price some options on the equity index. And here we make some assumption about the skew of the implied volatility and things like that. But the pricing options are not really so essential in this case. We just need something that looks like put and call options P&L, and then we perform some analysis to see how things behave. So after finding the price, the important point here is that the price is given with a notional of 1. So this is how we define these relative market values if you look in the article. After having the price, we just compute the options P&L. So this is just options with 1 year maturity. We compute their P&L at the 1 year horizon and add it to a P&L simulation. So before we add it, we just look at the payoffs just to see if they look like something that are put or call options, and they do so to me. And then here we add it to the P&L simulation. So here we then again use this simulation moments function just to get the statistics for the options also. And when you look here, then what you can see immediately is that the options have P&L distributions that are very different from a normal distribution. So for example, here a normal distribution would have a skewness of 0 and a kurtosis of 3, so you can see this is very, very far off. But even if you look at the log normal P&L simulation, then you can also see that quite quickly it starts to deviate quite significantly from the normal distribution. And of course, if you had real world data, then the statistic would be even more different than the normal distribution. Okay, so next here we just plot the P&L of the options just to show you that they have really, really fat tails. And then we get to portfolio optimization. So here, when we specify the vector of relative market values, first we add these put and call prices, and the important point here is that we price them with a notional of 1. So then we get this relative market value correctly. And then we add some just constraints on the individual exposures. For the cash instruments we say that it can only be long only, and then we have an upper bound of 25% on each of them. For the derivatives, we allow to both be long and short with up to 50% of the portfolio value in the notional of each options contract. So after that, we just extract the P&L simulation and put it into a NumPy array and specify a mean CVAR optimization object, where we use this alpha parameter to say that it's 90% CVAR. If we want to do this for variance optimization, well, then we can just extract the mean values and compute a covariance matrix and then input that into the mean CVAR class together with the constraints and the relative market values. Then we perform an optimization where we say that the expected return of our portfolio should be equal to 5%. And here we just compare the results. So the first thing you can do is just to verify that all the constraints that we have specified have been specified correctly, and they seem to be so. After that, we just look at some exposure and market values. So here we verify that the self-financing constraint is correct, while the exposures they can be different from 1. Another interesting thing we can do is just to plot the portfolio P&L. So here we see the difference in the P&L, how it looks for a 90% CVAR optimized portfolio and a variance optimized portfolio. So what we can immediately see for the 90% CVAR optimized portfolio is that scenarios where we lose a lot happen much less frequent than for the variance optimized portfolio. On the other hand, we have significantly more upside potential in the 90% CVAR optimized portfolio. You should remember that both of these distributions have an expected return of 5%. So here we just compute some risk numbers and look at how it looks, and then compute some minimum maximum values. Okay, so next we want to perform the same analysis, but then introduce some entropy pooling views and then see how it looks. Here I implement some views on DM equity. So I increase the implied volatility to 20%, and then I introduce some skewness and kurtosis views here. So you can see here in the simulation moment that the volatility is 20%, and then I have this combination of skewness and kurtosis. Sometimes when you just look at the combination of skewness and kurtosis, it can be hard to assess what that has really done to the distribution. So what I like to do is just to plot the distribution of the DM equity returns. So the prior distribution, which is just this log normal, and then the posterior. And then you can see that this posterior distribution that I've introduced some really nasty left tails in this simulation. So this is just to see what happens when we do portfolio optimization in that case. So here we again perform a posterior portfolio optimization, and you can see that the only difference here is that instead of using a prior probability vector with uniform probabilities, we just specify the posterior probability vector Q. And the same thing when we extract the mean for the variance optimization, we just extract from the posterior statistics, and when you compute the covariance matrix, we use the posterior probability vector here. And then we can do mean variance optimization again. So here we again say that we want a portfolio with a 5% return. Look at the exposures, verify that the constraints are satisfied, and look at the self-financing constraints and the portfolio exposures in total. So we then perform the same thing where we look at the portfolio P&Ls to compare how it looks. And basically we get the same results as before, that scenarios where you lose a lot are significantly less likely with CVAR optimized portfolios, while you have a lot more upside. And then remember that the expected return is 5%, even though the shape of distribution is quite different. You should also remember that these portfolios they use kernel density estimates to illustrate these distributions, so they are more smooth than if you did like a histogram, something like that. So it's also important for you to examine the numbers of these portfolio P&Ls more carefully, because sometimes the plots can be a bit misleading because they do some smoothing in the estimates here. But then finally we compare the volatilities, the variances, and the CVARs, and then maximum and minimum return and things like that. Alright, so this was the walkthrough of the fifth example, and as usual, if you like this package, if you like these videos, then I encourage you to give the GitHub repository a star, and then I'll see you in the next video.